Good morning, ladies and gentlemen. Welcome to this webinar, KNX webinar on KNX IOT, with the subtitle KNX, a great solution for smart things now and in the future. My name is Joost Temmerest. I'm Chief Technical Officer at KNX Association, and this is the agenda of today's webinar. First, I will explain you that, of course, smart things are, many people have different definitions of what they call smart, and I would like to use the use case of smart lighting throughout this entire webinar to actually try and explain that the Internet of Things and the solution to the Internet of Things may be very different and has quite a number of challenges that need to be addressed. For instance, the issue of scalability, the issue of different supported communication media, the issue of grouping, the issue of synergies with other application domains, the issue of ensuring interoperability and security. Then I would like to ask the rhetoric question, what does KNX offer for smart lighting already today? And how will KNX evolve in the future and ensure a smoother integration with IoT? I will inform about the different stages in the IoT development that we have fixed. I want to explain you what kind of devices will be involved in KNX IoT. I will explain how they communicate, and I will round off with explaining a number of other possible use cases that will be possible via KNX IoT. So let's get started with this webinar. And first of all, I would like to ask, what is your possible definition of smart lighting? Is a lamp already smart enough for you as a user if it is just energy efficient? So a smart LED light bulb, is this already your definition of smart lighting? Or should you be able to switch the lamp on and off via your smartphone as an alternative to switching it on with a wall switch? Or should this smart lamp also be able to have its color settings controlled via your smartphone? Is a smart light bulb smart because you are able to switch all lights off in one go when you leave your home or your building? Is a light smart just because it is able to communicate, to connect to the internet? What happens if this smart light is disconnected from the internet? Should it still work then? Should the light or the light fixture be able to carry out additional measurements compared to giving light or next to giving light? Should it be able to sense movement? Should it be able to measure the natural light intensity? And if it does, then should it be able to be switched off automatically? Should it also be a temperature switch? Should it maybe even measure air quality? How secure should communication to this light be? So should everybody be able to see communication to this light? Or should this smart light bulb also be able to report on any defects it has? For instance, that it has detected short circuits. Should such a smart light bulb also increase comfort, because it always ensures a constant light level? Should it also increase productivity, because it makes use of tunable white? So it optimizes office space on the basis of presence? Should this smart light bulb towards facility management, or should it report on its operating hours to proactively exchange it because it is past the number of normal operating hours it supports? So as you can see, there may be a lot of definitions of what you refer to as a smart light bulb. If you have a light that is connected, or if a light bulb is intelligent, how should it be connected? Is the light bulb a light bulb like we know it today? Is the controls of the light included in the lamp itself, or are the controls in front of the light? Regardless whether the controls are in or outside, which media should it be connected to? Should it be cabled, or should it be communication to the light be wireless? Is controlling of just one light sufficient, or should all lamps in my home be controllable, not only the light next to my bed? When you're communicating wireless, then you should be aware of the fact that one wireless solution is not comparable to another wireless solution, because a wireless solution could be using different frequency depending on the used technology, or even the country regulations. In some countries, a certain frequency can simply not be used because it's not permitted to be used in this particular country. So if you use different frequencies, then by physics, these different solutions are not able to communicate. So you would need gateways to make them talk to one another. And if you make use of gateways, then of course you increase the complexity of the installation. As a rule of thumb, the higher the frequency, the smaller the transmission range of your technology. So in some cases there will be a need for mesh technology to help messages getting from one sender to the eventual receiver. And there are many different meshing technologies to solve this exercise. If you would use the same frequency like a a very common frequency used for wireless solutions is the 2.4 gigahertz band, for instance used for Wi-Fi. But if you use also other solutions in this same frequency band, then you may run into the risk of congestion of the media. And of course there is the trade-off of the need for power. So if you would have this very energy efficient lamp, but you would add inefficient communication to it that uses a lot of power, then of course this is not a win-win situation. So can you make use, for instance, of battery powered sensors? Or is it even possible to use energy harvesting sensors? So sensors that do not need batteries, but they harvest their energy, e.g. simply by the fact that you press on the button. Or if you're not using wireless, why not connect this smart or these smart light bulbs to Ethernet and cable all these different light sources to one common switch. Currently there is with the Power over Ethernet++ solution, it is even possible to supply up to 90 watts, but there is a need to use different cabling than normal Ethernet, and you also need to use different connectors. And there is a higher power rating and current level that may lead to self-heating concerns. So random material touching the wire could self-ignite. If you read on the internet concerns about Power over Ethernet, especially when it supplies, when it can supply more power, then on the internet these concerns are of self-ignition. Ignition are these on the internet you can read concerns about that. Also, the topic of grouping of lighting is very important, because does the solution allow you to link anything to anything? So, of course, linking one sender to one receiver is a job that can be easily solved. But can you also link several senders to one receiver? Or the other way around, can you link one push button to several light bulbs, so that you are able with one press switch off all connected light bulbs? Or is it possible to connect several senders to several receivers? So in the case where you would like to switch on and off your multiple lights by means of multiple push buttons. Or is it possible that you link one sender to all receivers? So if you want to realize an on-off, an all-off command from one push button near the door when you leave the home, that you can switch off all receivers in the home. Of course, also the IoT solution there shall be no latency problem between receivers activating the light, at least not on room level. So, for instance, if you switch on the light of a big conference hall, the thing that may not happen is that the lights, there are delays in switching on the lights, in switching on the different lights. This would not be appreciated by the users. So the solution of grouping the senders to the receivers, this must be scalable up to many thousands of light fittings, because you want the same intelligent light bulbs to be used not only in homes but also in hotels, office spaces, public buildings, etc. And also very important, how can you see which sender is linked to which receiver? These links must be, it must be possible to make them visible and to document them. Because if you want to add another lamp to an existing group, you would like to first see the nature of this group. For instance, if two senders are linked to 7 receivers, you would like to visualize this or to see this in, for instance, a tool able to document the links between the different products of the different manufacturers. Of course, I have now, in the presentation, I have concentrated on the lighting application, but there is more than only smart lighting in buildings. There could be also the intelligent control of heating, ventilation and air conditioning. There could be the smart sun shading application. There could be battery storage. There could be a PV installation. There could be intelligent, typically in a home, there could be intelligent home appliances. So, would it not be a good idea to make optimal use of synergies between applications? For instance, a movement detector in a room can switch the light on and off, but it could also at the same time, with the same signal, control the heating, ventilation, air conditioning. It could tell the heating, ventilation, air conditioning that there is presence in the room, so the room needs to be heated or cooled. For instance, the intelligent shutter control could avoid unnecessary use of artificial light on bright days. But the intelligent shutter control could also avoid costly cooling of the room on sunny summer days. It could simply lower the shades to avoid bringing in excessive heat into the room. But the shutter control could also be protected in case of heavy wind, by a simple wind alarm. The e-car, for instance, could be charged when energy costs are low and the solar production is high, etc., etc., etc. So, in a home and a building, there are so many applications that can make use of each other's data to make the smart home or the smart building even more smart. But in case you couple all these applications, of course, again you have the need to document the bindings between the different products and the different manufacturers. And here there is really a need for a trained system integrator able to know all the features of all these applications and really couple them well together. If you look at the current Internet of Things, is mostly concentrated concentrated on the communication between one thing and another thing. But mostly the solutions are provided by one manufacturer, and products of different manufacturers, they do not really provide interoperability. So how can we make sure that all these products talk the same language? And how to ensure that the communication stacks in all these different products, they are backward compatible, so that an old product can be combined with a newer product? And how can you ensure that all these protocols, they also foresee standardized mechanisms for linking products of different manufacturers? And how do you ensure that this technology is platform independent and royalty free? And that the products, when they encode useful data, like the sending of a temperature or sending of a dimming command, that they all encode this useful data in the same way for all products. And how to make sure that if manufacturers use proprietary coding, that the use of proprietary coding is kept to the bare minimum. How can you also make sure that if you have an intelligent or smart building or a smart home, that inside the building or inside the home, there is not a possibility that an intruder, a hacker, gets easy access to the data that is exchanged between the products of the different applications and different manufacturers. If the data is also transferred to the cloud, how well is this data related to your smart home or your smart building protected against unwanted tampering or data mining by third parties? So how are you sure that the data, if it is put in the cloud of your smart home manufacturer, that your data is not misused? And how easy it is that a hacker uses the internet connection to your home or your building for causing unwanted behavior of your smart home or your smart building. Well, there is good news. There is already a solution on the market which is called KNX and ticks all the previous boxes. KNX, in a KNX installation, it is possible to include 65,000 nodes in one single installation. There are different media solutions supported. The common solution is a twisted pair network, which is depicted here. There is also the possibility to use a common wireless solution based on 868 MHz. There is also the possibility to run communication on existing power line networks. And there is also the possibility that through IP routers, these different segments are connected together to form a fast IP backbone. There is the possibility to authenticate and encrypt communication on twisted pair and radio frequency and IP based on AES 128. There is the possibility to couple power line and radio frequency in a standardized way, and also to couple twisted pair to IP in a standardized way. Also, the configuration of devices, of KNX devices from different manufacturers and different applications can be, so the commissioning can be done by one single tool. This tool allows you to design projects. It allows you to commission the included devices, and it also allows you to diagnose a KNX installation. All of it manufacturer and application independent. All the project information is stored in an openly described XML-based format. The tool supports also KNX secure devices, and it is available in 2 different flavors. It is available as the ETS Professional. The ETS Professional allows you to commission and design a maximum size KNX installation, which can have these 65,000 nodes. This version needs to be installed on a PC. So the ETS Professional is exclusively for use on a PC. And there is also a version that can be used on a mobile platform like a tablet, for instance. This version is called the ETS Inside, and the ETS Inside is especially intended for newcomers to the KNX technology, including end users, but it only allows to design and commission a installation with a maximum of 4 times 255 devices. So typical for home and light commercial installations. So you see a snapshot here of the ETS Professional, and you see a snapshot here of the ETS Inside. KNX really does provide proven interoperability. KNX products have been backward compatible since 1992. So it means the very first KNX devices can still be combined with a new KNX product from the year 2017. If the product shows the KNX trademark, which you see here on this ABB product, then this means that this product has been certified. And it has been certified because it has been tested by a third-party test lab. The manufacturer can unfortunately not make use of self-certification. The product needs to be sent and tested by a third-party test lab. The protocol, the KNX protocol, can be implemented on any microcontroller and is totally royalty-free for KNX members. The linking and configuration of products is part of the certified stack. So the communication with the ETS software is also part of the certification. All products make use of standardized coding for standardized functions. And proprietary coding for useful data is only accepted in very rare cases. More than 400 manufacturers already offer more than 7,000 certified products for many application domains. And approximately over the 25 years of existence of KNX, approximately 250 million nodes have already been installed worldwide. In more than 300 training centers, you can attend a KNX certified training to become a KNX listed certified KNX partner. And there are nearly 75,000 listed trained system integrators worldwide. Of course, this was an introduction to show you that KNX already can be a perfect element in the Internet of Things. But in the second part, I want to show you that KNX is an integrated part of the Internet of Things, but its integration could still be improved. And by the next 10 or so slides, I want to show you how KNX intends to make this integration in the future even more easy than it is today. But first, I want to explain you that the current KNX Classic has, as regards semantics of the data, it is quite limited. It is quite limited as this brings advantages, but it also has some disadvantages. If you look at a KNX message that is sent from a sender today to a receiver, so for instance a switch to a actuator controlling a lamp, then this message is completely data driven. If you look at the message from the bus, it is not possible to determine what the data actually means. So in the message which is sent, it is not said, with this message a lamp will be switched on and off. No, the message just simply says it is sent from this device with this individual address. It is sent to this group address, and the binary data that is sent is a 1. So you can see it like this: the sender and the receiver have a shared pre-knowledge. The sender knows the meaning of the data, and so does the receiver. The so-called data point types that are specified in the product data of the different products, the data point types, they give meaning to this data, and the electrician is trained to connect data point types of the same type. So the data point type switching of a sender and the DPT switching from this actuator, the electrical installer will connect these two functions together because he knows that these two functions they are compatible. Because of this, and without the ETS project, it is unfortunately not possible to know that the address 111 is actually the push button in the master bedroom, and that the master bedroom is on the first floor. And the group address 111 stands for switching on the light in the master bedroom. This data is not visible on the bus, and this data is only stored in the ETS project. It's not stored somewhere in the installation. And without the knowledge of the KNX standard, an outsider can also not understand that the coding 1 means switch on, but for a blind actuator, a 1 also means move down. meaning the data-driven approach, the meaning of this data is actually, again, it's a shared knowledge between the sender and the receiver. This brings a lot of advantages because a lot of coding can be reused, but as you can understand, the semantics in this solution is at best in the part of the ETS project. So today there are existing solutions that allow you to connect a KNX Classic installation to the internet. This solution is called KNX Net IP. It has already been on the market for more than 15 years, but it actually was not designed to connect a classic installation to the internet. It was designed for fast backbone and tunneling solutions between a PC and an installation, and it actually was intended to be used on the local area network only. The solution also does not include discovery and connectivity in a secured way. So if a web client wants to connect to a classic installation, then there is no uniform way of discovering this installation. So if you want to make this solution secure over the internet, then you must make use as an installer of VPN tunnels, and you need, as an installer, you need a lot of IT knowledge. And what you have to do is, if you use this solution which actually only tunnels the previously explained message over the in an IP telegram, then you need to re-enter all the project data again in the web client. As you can understand, this solution works, but it's very KNX specific. Also from our manufacturers, there are a lot of manufacturer-specific solutions. Actually, the manufacturer-specific solutions, they do not make use of KNX Net IP, but they use a manufacturer-specific IP protocol. So this manufacturer-specific IP protocol has the advantage that the web client can make use of HTTP to talk to a manufacturer-specific gateway, which then transforms these HTTP commands into KNX messages. But of course, the protocol is very KNX, very manufacturer specific. So if you want another web client to understand this protocol, then of course this will not be possible unless you install the manufacturer specific app on this web client. And again, also the same disadvantage exists as for KNX Net IP. You need to re-enter the project data that is contained in the ETS project, again also in the web client. So also this is not an ideal situation. In 2016, KNX has already made available a solution which hoped to already resolve some of the issues I have explained in the previous slides. The KNX Web Service Gateway, so the KNX IOT 1.0 version, which was launched in 2016, already standardized the application layer protocol that is that was talked between the web client and the standardized KNX IoT gateway. This specification extension is documented in application note 175 and allows the use of OBIX, OPC UA, and BACnet web services as application layer services to talk to the standardized gateway. However, so the standardized gateway could be fed in by means of a ETS app with the data contained in the project. However, this KNX standardized information model was still only tag-based. And the meaning, so the semantics of the data, was still pretty limited. Also, the security and connectivity to the gateway of the different manufacturer was still manufacturer specific. There is a free of charge proof of concept available in MyKNX, which is provided by KNX Association itself, and this solution is already part of the 50090 European standard as part 6-1. So already today there is a possibility that the web client is more synchronized with the web server. However, there is still the possibility, or there are still three flavors of the application layer. There is OBIX, OPCUA, and BACnet. So a OPCUA web client can, of course, not speak with a BACnet web service based web server. So in order to remedy some of the shortcomings of the KNX IoT 1.0 solution, KNX is currently working on the KNX IoT 2.0 solution, where we will define an own application layer protocol. So there will be, next to OBIX, OPCUA, and BACnet web services, there will be a uniform application layer protocol as well to exchange data-driven KNX information in IT protocols. And we want to include rich semantic data which we would like to export together with the ETS. And the security between the web client and the web server should be according current IT standards. And this rich semantic data is part of the KNX IoT resource model that is that will be documented as the KNX IoT ontology. This KNX IoT ontology is created with RDF triples, and we have already designed a visualizer to create a visualizer to browse the model, and the model is available as a turtle file to KNX members. The KNX IoT project information will be communicated, will be exchanged based on JSON LD, and the IoT runtime data will be communicated based on JSON LD or JSON or CBOR. And also for this project, we have already submitted in international standardization a new work item proposal, part of the 50096.2. In KNX IOT 3.0, which we want to launch in 2020, we want to also be able to have KNX devices that are fully based on IP media, like Thread or others. Next to the possibility, of course, to continue to create KNX products based on twisted pair and radio frequency. The communication between these fully IP-based devices will be based on HTTP or CoAP. They will use IT security for their IP communication, and KNX will also certify this and guarantee interoperability between these different devices. So which kind of devices will be involved in the KNX IoT solution? This picture shows you two halves. The first half being the communication inside the building. The second half, the communication on the internet. In the building, there could be a KNX IoT stack. There could be so-called KNX IoT capable devices, devices that typically have more resources as regards power and as regards storage of data. These devices would typically communicate or use for their communication TCP and HTTP. They would use TLS security, and they would make use of or they would use or encode their data using JSON LD. This constitutes a classic KNX network, with, of course, which could be based on twisted pair as before, or KNX radio frequency as we know it today. The connection, the twisted pair network would be connected to IP via a KNX IoT 2.0 gateway. Possibly there could be two of them for failover. Another section of the network could be KNX IoT constrained devices. So constrained devices are the opposite of capable devices. They don't have a lot of resources, and possibly they also are battery powered. So these devices could be based on or use Thread as a communication medium. They will use for communication 6LoWPAN, UDP, and CoAP. The group security would be derived from our cooperation between KNX and the Fairhair Alliance, and the useful data would be typically, or the serialization of the data would use CBOR. Such networks would be connected through a border router to the other for further IP communication. So the right half of this border router would be communicate via Thread. On the internet side, there would be notebooks, tablets, phones. There could be a cloud server, and there could be a KNX IoT stack sitting in the cloud. And there could be a KNX IOT stack that also on the internet that combines the information on the KNX ontology and the project information. All parts that of this network would be optional. They could also be temporarily unavailable, but even if parts are temporarily unavailable, locally everything would continue to operate, and the historic data will be taken into account after the parts are restored. How would devices communicate? For instance, on a KNX twisted pair network, of course, this communication is well known. So the sensor would say, I'm 111 and I sent the group address 111 and the data is 1. So this would reach this actuator. This actuator would, of course, know that it listens to group address 111, and for me, I know that this is a switch on command. This IoT 2.0 gateway would know that group address 111 corresponds to the metadata ID 123. It would send this on this IoT backbone, and this device, for instance, would say, I don't really know what this meta ID 123 is, but I will look it up in the KNX IOT stack in the cloud. This IoT stack would then say the meta ID 123 refers to a function which is defined at knx.org/lighting/switching. According to that function, the one means switch on. A building structure element that is defined at knx.org location/room. And in there is the possibility to see that this room is of the type bedroom. There would be the possibility to browse and detect that the name of the room is master bedroom. And the client could browse for more linked data if it wanted to see more of this linked data. So, because it has been informed about all of that, it can now show in the floor plan of the building, in the visualization, that the lamp in the master bedroom was switched on. On this network with capable devices, this message could also be forwarded. On there could be a powerful display that knows what meta ID 123 is, and because all of this data is already in its memory, so it could immediately show in the floor plan of the building that the lamp in the master bedroom was switched on. On this thread, field bus IP system, this border router could also, from the project information, know that there is a device in this network interested in the information sent by the classic device, so by this sensor. So it would forward this message on to the IP field bus. Then this device would say, I see on the shared multicast group a message with an ID that is configured to the functionality I have for immediate reaction by all the devices within the multicast domain. So I react data-driven, just like any KNX Classic device. And for reliability, I will also get this message unicast for acknowledged tracking. So it will then also switch on this light. Other use cases could be I'm a GSM and I'm turned on. I'm interested in being notified when a light is turned on while the alarm is active. I send this query with this requested information to an IoT endpoint. In this way, I will get a notification with semantic information included. So the message contains master bedroom light on and alarm active, and the rest of the project is of no concern to me. So if I receive this this message, master bedroom light on, alarm active, then I will perform the action that is programmed in my user interface. Another possibility would be that I am a cloud server and I'm an external governmental cloud service, ensuring that public buildings are run energy efficient. I request KNX IOT to put the HVAC mode to economy if the average temperature of the last 24 hours measured is above 18 degrees. One KNX IoT server that has collected the data measured by the sensors concerned will check this historic data against this request. And if it's fulfilled, then it sends a data-driven message to the relevant building. So what is the intended KNX IoT architecture? So which communication stack-based protocols will we use, and with which other alliances do we hope to are we cooperating? So for constrained devices, as I explained you, we, for instance, will use for the wireless solution Thread. We will communicate through 6LoWPAN, UDP, and co-op using DTLS security. We will use KNX IOT data-driven with linked data semantics. For this, we are cooperating for this building automation technology based on RDF triples with BACnet and also with Haystack. In the end, we wish to standardize this building automation ontology also through ISO TC205. For this constrained stack, we are cooperating together with BACnet and ZigBee in the Fairhair Alliance. And for capable devices, we want to use the commonly used media that are available today. So, for instance, Wi-Fi and normal Ethernet. We would use TCP and HTTP and use TLS security. Here we would use IPv6, but also we would also allow IPv4 based solutions. So all of this to summarize what the architecture will be of KNX IoT. So in summary, KNX is truly an investment security because KNX Classic will be seamlessly integrated into KNX IoT. Many thanks for your attention, And for more information, you see here my email address. Thank you very much.